we're talking about Schrodinger's equation, and what we're getting into this idea of a wave function. And we left off with waves, how light can act like a particle when it wants to, or act like a wave when it wants to. It just depends on the situation that seems to determine how it behaves. So that means that all matter must have some type of wave nature to it. So this idea of the wave function is coming out. And where this all really comes down is, I think, statistics. It's really hard to find concepts out of this. I'm going to dig and crawl and scratch to help us relate to this, but when it comes right down to it, it's just very abstract and very obtuse, and hopefully we'll have time at the end of the semester to watch some movies. I think Ricky, you already saw them, didn't you? Didn't you sit down? Saw one of them, right? So they help a lot. But you pretty much have to go through all this first to have an inkling of what the heck the movies are talking about. So we'll get started here. We have the time independent. So that means time doesn't even come to play, right? There's no t in the equation, and that's how we're going to be doing things. I think someone mentioned something about how time evolves, and that's just a whole nother parameter. And we could put that in here. What are the energies at specific times? But man, it's enough work just to figure out what the energies are static-wise. So we're just going to leave it at that for now. And I think that's much more advanced classes. But I think we'll get the idea. If you apply time, computers are going to be doing all the work by that point anyway. So we have this. So we're talking about an electron. So that's what the little m is, the mass of an electron. And then they have this h bar. That's just Planck's constant divided by 2 pi. To save them some writing. That's what h bar is. And this is in one dimension. So what this pretty much means is we have an electron in one dimension. So one dimension would just be a line, right? And that electron is somewhere on that line. And this wave function, that's the idea. It's going to tell us where it is, its likely positions, its possible energies, all that kind of thing. And that's where things start getting weird, is it can't take on an electron. It looks like a ball on this table. Why the heck can't it be anywhere? Why the heck can't I roll it any direction, right? Why the heck can I roll at any speed I want, all that? No, all that's out the window. That lousy ball can only be on certain locations on this table. That's just how nature is. That lousy ball can only roll at certain speeds. That lousy ball has a possibility of being outside that wall. How? The ball can't even fit through the wall. There's and that probability has to exist. If you don't include that possibility, you get all the wrong answers. So it does exist. I mean, if you've heard of tunneling microscopy, MRI, all these machines are doing energetically impossible things. It's relying on quantum mechanics to work. But anyway, so this electron has to be somewhere on this line. I just drew a line because it's one dimension, just x. So, but that's anywhere. So that's not really much of a problem. I mean, the electron could be anywhere. The line goes on forever and ever. But bonds aren't like that. Right? You have a nuclei here and a nuclei here. We've heard of bond length. I mean, these are specific distances. So that's what we're going to do. We're going to say, nope, not a complete line. There and there. Has to be in the box. Okay. So x actually has a beginning and an end. There's actually limits. And we'll talk about that in a little bit, I think. But that's kind of where we're headed. V of x, that's the potential energy. Potential energy function. And that's going to be really, it really complicates matters. This potential energy function does. So at the beginning, when we're just learning the fundamentals of quantum mechanics, we're pretty much going to say, there is no potential energy. It's just that flat line. Like it's the same energy everywhere. But you know that's not the case, because in a bond, you have a positive nuclei here You have a positive nuclei here, right? It's not going to want to go either way. And the more it goes this way, it's more potential energy. It's going to slow down. Kinetic energy is converted into potential, right? It has to stay on that line. So very often we're going to just kind of be in our wonder world and say, oh, no, there isn't any. Just have our borders. Okay. And they're just infinite. They're just a wall. Okay, that's what will happen a lot. So V is potential energy. E is the total energy. Typically, there's usually two types of energy things are divided up into. Pablo, you remember what they were? Typically, you either had this type of energy or this type of energy. Kinetic and potential, right? Energy of position or orientation, potential energy. Motion, energy of motion, kinetic energy. So total energy is going to be our E. Okay. So what's the magic thing that gives us all of this? It's the wave function. Now, not any wave function is going to work. You have to use the wave function that's going to give you the right answers. Okay, and there's going to be certain properties to it. Okay. If you didn't want to be on a line, if you wanted to be, I don't know, how do you draw 3 dimensions here? Right? X, Y, Z. If you wanted to be, and so our 3 dimensions, X, Y, Z. So what's the, now we're talking about, instead of a position on the line, we're talking about, I don't know, a little cube in space. Right? This little x, dx, dy, dz, this little, right, little cube. So now that electron is there. So that's the only way to describe its position, right? X, Y, Z. Here we just had X. So this will, it's the same, exact same idea right here. The E is the same, each bar is the same. Okay. Just more math, more complicated. Okay. And we'll talk about what del squared is. Okay. But essentially, you just put in the right wave function, and you can get the energies for that electron. Okay. Given its boundaries and giving its potential energy. Okay. So wave function. Just some general ideas of how things that you can't do with these wave functions. These are no-nos on wave functions. So pretty much what happens is a computer, you already played with Spartan a little bit, and a computer, that's all the computer's doing is messing with the wave function and trying to get, because it knows what the particular energies are, and it's just going to keep modifying the wave function to try to minimize the energies. You know, lowest energy is the ground state, so if you have the wrong wave function, you're going to calculate too high of an energy. That's pretty much what happens. And we'll talk about how computers are messing around with stuff. But you can't have it. See here, this wave function is discontinuous. It's here, then it's there, right? Here it's got this changes slope so quickly like that. Can't do that. Here it's in the same plate, same position, same value of the wave function for the same value of x. Right? Here's blowing up to infinity. You can't do that. So just no-nos on the wave function. Okay. So pretty much all we're going to be using is the sine or the cosine wave. That's all we're going to be using. Yep.
The wave function is considered time dependent.
You can consider it time dependent. We don't have it written up here. How do things evolve over time? But we're not even going to mess with time. So don't even worry about time. Time is, and really it's okay not to worry about time. There's so many problems that involve if you have it can be really difficult to synthesize these anti-tumor, anti-cancer drugs. It can be really difficult. So why not just do everything on the computer, right? And you know you have the right answer when you get these minimum energies. So the right, especially orientation. These things are getting huge and they're getting complicated. So if you get the right orientation, that's a big clue. For example, I remember we were working with these intercalator anti-tumor drugs, right? They intercalate into DNA between the base pairs. And a lot of that was just moving one OH group around this complicated ring or moving a carbonyl or something and seeing how the interaction changed. So all you're interested in is when you get these minimum energies, you know you're on the right track. So all that, nothing had to do with time. You're just calculating, you're minimizing your energies. And that's very often what happens. You get a lot of information from it. Okay. Yeah, so let's not worry about time, right? Not right now.
So then, and I'm sorry, blow on this. Then what is the wave function being?
So I think what you need to get out of your mind is when I draw this, I'm not drawing, you're thinking of a wave going from here, going to there. No, a wave exists. I mean, you don't know where. That particle is somewhere. This wave function starts and it ends. It doesn't, where does it stop? Where does it end? It doesn't have a beginning, doesn't have an end. It just keeps going on forever and ever. So there is no time involved at all. It's kind of like, think of a plot. You put it on the computer. You get this big plot of this function. There's no time in there at all. It's just, that's how it is. Right?
So
At that.
So that's when they say we treat a particle as a particle and as a wave.
We're not quite, I need more time to get there.
Okay.
I need more time to get there. Okay. So we're just, right now, think of this as a function. A function, right, just exists. There's no time in it at all. The Born interpretation of the wave function. Okay. So it's really I don't think you even can apply any concept, any relation to our world right here to the wave function. It's just, it doesn't make, it's hard. I can't relate to it. But I can relate to this Born interpretation of the wave function. Because what that means is if you take something called the probability density, that's supposed to be an n. If you take something called the probability density, you can find out where the particle is. Okay. And what you have to do, is take the wave function times itself. But the first wave function has a star, and that means complex conjugate. Okay. Yeah, that's right. I wanted to do a couple of these. Okay. So complex conjugate, what does that mean? So let's say a wave function is, I don't know, e to the I kx or something. You might see something like that. K is that, you remember in physics, they had the spring constant. They often use K for it. So we'll see that coming up. But complex conjugate just means look at your wave function, and wherever you see the complex number, which is represented by what symbol? I. Replace I with minus I. So if psi, let's say psi is e to the ikx, then psi star would be e to the negative ikx. Just replace I by negative I. That's all it means. Okay. So if you want to find out where where a particle is, find the probability density. So up here on this line, if we want to know where the electron lies on that line, and again, it's just a very odd thing. Why can't it be anywhere? It can't. It depends on its energy. So if you want to find out where it is on that line, you have to find probability density. Take psi star psi of the wave function. This is their shorthand notation of representing psi star psi. Okay. Kind of like the magnitude of the wave function squared or something. Okay. Notice this is, I think we're jumping into 3 dimensions now. Yeah. So here they wrote d tau. So if you wanted to do just 1 dimension, it'd just be dx, right? But if you have 3 dimensions, it's d tau, dx, dy, dz. So where is this particle in space, in this unit volume, right? So you could say, I don't know if I can write small enough, but you have a little dy, right? Because volume is length times width times height. So you have a dy, you have a dx, and you have a dz. That's all really d tau is. Okay? You're going to see that a lot when we're messing with these integrals and finding probability density. You could either have a dx if it's 1 dimension, or a d tau if it's 3 dimensions, because you want to find the probability of it being in that volume if it's 3 dimensions. Okay. So let's say you have this is x, and we want to know what's the right? Oh, I'm trying to just make what would it look like if it's 1 dimension? Right? If our box only goes from 0 to 10, so we know that it has to be in there. That little electron has to be on that line somewhere between 0 and 10. So if I find the probability density, it has to be in there. So they're going to say not 100%, they're going to say that's 1. So 1 means 100%. Now this is where things get funky. Let's say instead of going from 0 to 10, I go from 0 to, I don't know, 3. Well, you'd think the answer might be a third. It might be if it's linear relationship, but weird things happen. But you get the number in here. The probability of it being between, you could pick any 2 numbers, 0.25 and 0.7. Right? Really narrow. If you're really interested in that, what's the probability of this electron being found within these 2 positions? You just find psi star psi. You get your number. It'd be probably really small, like 0.09 or something. So that's the only game you're playing, right? Between 2 and 8. Just put in your limits, wherever you're interested in. Okay? So how do you find the probability of an electron being somewhere? That's probability density. Okay? Just integrate it. And we'll be playing around with that, so you'll get used to it. Okay. Now what it's... Okay. And here they're just trying to show you what it looks like, right? If this is my box that I was drawing between like maybe x equals 0 and I don't know, x is some length L, okay? And this is my wave function, that's my psi. That's supposed to be my wave function, right? And then my probability density, the peaks just kind of get sharpened up, but everything's positive, right? These are negative values of the wave function. We multiply negative times negative, you get a positive. So it just ends up looking like that. If we had, you could draw a bunch of these. You could draw a cosine function. Just keep that going on. I can make it longer here. May go on and on and on and on. Right, so that's my wave function. If I want to draw draw the probability density, you just have to square it. Multiply it by itself. So pretty much where these things, where you have 0, it's going to stay at 0. So if you're going to sketch it, the probability density, make sure you go back to 0. Because see where the zeros match. So that's really the only trick. And then you line up the peaks with the peaks. So I'll have a peak here. All right, I got to have a 0 here. Have to have a 0 here. Have to have a 0 here, so I don't screw up. Right? I have to have a peak here, peak here, peak here, a peak here, peak here. I'm probably drawing it too high and not sharp enough, but that's the idea. Okay. And what is an integral? It's the area under the curve. So the area under this curve is the probability. That's all you're really getting, right? Area is probability. Good. The area is probability. So that gives you some shortcuts. If this is my box, I don't know, right here, and since it's this nice cosine function, I've got 1, 2, 3, 4, 5 sections here. Now you can kind of divvy things up, and you can see what it looks like and make generalizations. If I plot it right down the middle, if this is my case, I'd have half the area. So the probability of the particle being in the left-hand side of the box or the right-hand side of the box is going to be the same. They're both 0.5. Just depends on what the wave function, what the probability density looks like. Make sense? Okay. Now, if you don't, this is where you think life would be straightforward, but it never is, right? If I say the probability is 259.8%, that doesn't even make sense, right? The probability of 100% means something's going to happen. 10% means, one chance out of 10. So we need to normalize to 100%. Otherwise, when we get our areas, there's these funky numbers that, if you stuck with that question, you would be used to saying, that 100% really corresponds to 206.9%. But the point is no, everyone's 100% is 100%. So we need to normalize all of our wave functions, what I'm trying to say, so we can communicate. So that if you add up all the areas under the probability density, you better get what number? Ricky, if you add up all these areas, 1, 2, 3, 4, 5, we better get what number? What number do we say corresponds to 100%?
Is it just one?
Just one. And that's what we're trying to do. We want to add up all the areas and make sure they correspond to 1. That's what normalization is. So we can't just write any wave function we want. We need to write our wave function. Right, here's any wave function we want. They call this phi. Any wave function you want, call it phi. Now remember, you need to obey these guys pretty much. If it doesn't have this stuff, it'll work. It may not give the best answers, but it'll work. Okay? So just make sure, pretty much cosine sine functions are what we're going to be working with all the time. So any wave function you want, if you make that your wave function, you can get all your areas and everything's going to be nice, but you're not going to get the 100% equal to 1. So let's normalize it. You put this, it's just a constant. They call it the normalization constant. Put that out front. Okay.
So the wave function equals
n times phi. So then you find n by setting this equal to 1. So it would look like 1 has to equal our integral, right? of n phi star n phi. Right? Because I said that here's my psi star, here's my psi. So that's pretty much how it works all the time. So the homework is going to give you some wave functions. They want you to normalize it. So what you do is, what I always do is I write this first. Normalize some wave function, they say. Okay, well I write this first. Otherwise I forget to stick in my stinking little n. And then I jump to the probability density equation and just substitute it in, right? Because we know that 1 has to equal the integral over all space psi star psi d tau, or dx if it's just 1, if it's just one dimension. This always has to, you want this to be true. And the only way to get it true is to normalize it, is that these wave functions have to be normalized. Because over all space, it has to be in that box. Whatever your limits are, whatever you're gonna put in here, whatever numbers you're gonna put in there, whatever the limits are, right? You want the probabilities to make sense. And if we're going to integrate over all space, well, we better get 1 because it's got to be somewhere. Whether it's a line or whether it's just in space somewhere, 3 dimensions, it's got to be there. So the probability has to be 1 if you integrate over all space, right? You could say negative infinity to positive infinity, make it look better, right? Negative infinity to positive infinity, it has to be there. So our polar coordinates, one more thing before we move on here. Oh, I want to do that one together. It's going to be, they're going to have us work in 3 dimensions a lot. And when you do integrals with dx, dy, dz, it gets really ugly. But we can use a lot of our little trig relations and integrals and things if we use spherical polar coordinates. Okay. So in our limits, we just have to realize where they go from, right? R goes from 0 to infinity. I forget these. Theta, I think they're on the cheat sheet. Theta goes from 0 to pi. And phi goes from 0 to 2 pi. Okay? So let's try one of these together before we move on here. Some space. Okay. Yeah. Let's say phi. Oh, does it still work? Yeah. Phi is e to the negative r over a naught. Okay. And the book just says write a normalized wave function. And sometimes they're not even consistent. They might even say this. Normalize this. I don't like it because when you write this psi, their notation means that that is a normalized wave function. So it's kind of poor, but you know, we get lazy with our, you should write this because that's an unnormalized wave function. Okay. So, and they don't tell you the limits. They don't tell you much of anything at all, except that little a naught is just a constant. Okay. So if you want to write a normalized wave function, you know it has to look like the answer is going to be that times what, Ashley? Yeah, n times the phi, which is going to be this thing, right? Yeah, n times the phi, which is n times the e to the negative r of a naught. This is going to be our answer. We just have to find this. And then we'll have our answer. That's all we got to do. So how do you find it? You set up the what density? Probability density. Okay, so again, I gave you these relationships. This have to dawn on you when to use them and how to use them. So 1 has to equal the integral over all, well, let's just write it the general way. They said that that's psi star psi d tau. This is your starting point. So we just substitute in. So that means that 1 has to equal, this is where you got, the book just assumes that you realize this. What realm are we working in? Our d tau, is it going to be dx dy? It can only be one or the other. Is it going to be dx dy dz, or is it going to be this thing? Which one is it going to be? Is it going to be the dx dy dz, or r squared dr sine theta d theta d phi, if you're in spherical polar coordinates? Which realm are we in if this is our wave function?
Just x.
I don't see an x, though.
So you don't assume your first one's x.
Oh yeah, there's an R in there.
There's an r in there, right? You don't. If you see an x, then you see a y or you see a z, you're good to go. But there isn't. This is written in spherical polar coordinates. They never tell you that. So you have to look at the wave function and kind of figure it out on your own. I see an r. Now, I don't see a theta or a phi, which I like, 'cause there's less to integrate then. So, but I see an r. So I am in spherical polar coordinates. So my d tau is that mess. And you don't have to memorize this stuff. You just got to look it up. This is the d tau that I have to use. So let's write in everything so we don't forget anything. We'll have our triple. I'm not going to skip anything because it's triple integral. We have r, which goes from 0 to infinity. And then what were the other limits? Theta went from 0 to pi. I should have wrote smaller here. Theta goes from 0 to pi. And my last little phi goes from 0 to 2 pi. Too bad they're kind of redundant on. Okay. There's my 3 integrals. Now I've crammed all my stuff in here, psi star psi. So what would that look like, Richie? So now I want to put in this stuff. Because I have the 3 integrals written. I haven't written d tau yet, but let's just kind of follow this order. So how would you write the psi star psi part now? So you have to write the wave function twice. If you see an I, replace it with minus I. Yeah, don't forget about this guy, though. Right? So it would be only if you see an I. Only if you see an I. N times e to the negative r. Yeah, it's supposed to be an a over a naught. N e to the. Is there an I? No. So negative r over a naught again. That's what complex conjugate is. You have to have an I. Replace I by negative I.
So pretty much if you don't see an I, then
Just write it twice. Psi star is the same as psi.
So you kind of disregard the star.
Yeah, yeah. Okay, now finish this for me, Brad. Now I have to write my d tau part. What would the d tau be? So I have my psi star psi. Now I'm ready for d tau. Yeah. Flip over a page. So this, you don't memorize this.
dx dy dz.
But we're not in x, y, z. It has to be the other one. R squared.
Yeah, so you flip it.
Do you see it? Right here. So it has to be one of these two. D tau has to be one of those two. And we have to pick this one. Because we have an r in our wave function. So we have to be in spherical polar coordinates. So it's, what is it? R squared dr
Sine
sine theta
d theta,
d theta
d,
d phi or phi. Yeah. Okay. Good. So to me, that's the hardest part, setting this darn thing up. And once you do it a bunch of times, you get used to it. But you pretty much start, and this is where writing a little bit extra really saves your behind. Write this stuff. Write down what a normalized wave function looks like. Write down the probability density equation. Otherwise, thoughts just get lost, right? These are just stuck in my head. I don't even, and if you think this way, life is so much easier. You don't care how complicated something is. You're just going to multiply it by n, and that's your normalized wave function. You don't care how complicated something is. When you want to normalize something, just write 1 equals the integral psi star psi d tau. Doesn't matter how ugly it is. Those are your two starting points. And then the math, well, we've practiced it already. How are we going to handle this, Pablo?
Separate all the.
What's the first thing you should do?
separate into your 3 variables.
Into your 3 integrals, yeah. Get all the r's together, put it in the dr integral. Get all the thetas together, get all the phis together. And if there aren't any, great, let's integrate.
So the first one will be your R and
Yeah. Yeah, it really doesn't matter because 6 times 3 times 2 is 2 times 3 times 6. The order doesn't matter. But you might as well stick to it because that's what we have. R is 0 to infinity. And what would be in there? This is the only ugly one.
the e to the negative
Oh, good.
r over a naught.
But it's really this one times this one, isn't it? What would
Yeah,
that
so
be?
it's e to the negative 2 over
E to the
because you add them together.
add the exponents.
Yeah.
So negative r over a naught plus a negative r over a naught is a negative 2r over a naught. Are there any other r's?
Yes, the r squared.
The r squared. So let's put that there and that there. There, we have that one. Hopefully it looks familiar to you.
So the n is in the
Oh, we forgot it, didn't we? Oh, what is n? Where should we put the n?
It's a constant. So
N's a
it's all the way
constant.
outside.
Yes, let's do that. Thank you, Ashley. Let's pull it all the way out here so you don't have to worry about it. It's going to be n or n squared.
And then use the big brackets, I guess.
Yeah, you
right?
could,
Or
yeah.
Put it in front of each one.
Yeah, it doesn't really matter. Just so you only have one of them. Okay, now we have theta going from 0 to pi of, I don't know what, Richie? Do we have any thetas? Well, have you got a sine theta? Anything else? Yeah, that's about it. We're done. Okay. And then phi. Ashley, how about our phis? What am I going to put inside the integral there? Just what? Yeah. I guess a 1, but that's it. We did all this in the concept preview. So this can be a you do to finish it, but what I want to show you is 1 is going to equal n squared, and then, I don't know, you have to do those integrals from the concept preview. And this, I think what we were supposed to memorize it, and I already don't even know what the hell it was. Remember? Anyway, it's like 2 pi, or I forget what the answer was. But this part, remember? I said, oh, just know what, then you have to do it again. I don't remember what the hell. You're gonna have to figure it out, just like I would have to figure it out. So, but the point is, you're going to find it. You can put it in the brackets. And then you bring it over to the other side, to get n, you have to take the what?
I'm sorry, what was your question?
Because we want to find n.
Uh-huh.
So then it's going to be
Take the square root.
By everything
take the
equal
square root.
minus square root.
Exactly. You're going to have to take the square root. 1 over your brackets, square root is the same as a half. So then write the normalized wave function. Finally, you can get your answer then. Your answer is going to be capital Phi equals, I guess you'd have to write this thing, whatever you get.
Do that stupid integration by parts on that one.
Yep.
No.
Oh, okay.
There's an easy way. You could. You could integrate by parts. Concept preview.
Oh, it's that 1E equation with like
Oh,
the
that's
n.
good.
You have a
Oh,
factorial
I'm
or
so
something in
pissed
there?
off at that thing. I'm gonna just remember that.
It's in there.
Freak
It's
out.
in there, so you can get it out. I hope it's in there.
That just meant for the last integral. Would it just be phi or?
Let's do that. Okay, so 1 equals n squared. Okay, well that's that concept preview part.
Yeah.
This one is going to be what evaluated from 0 to pi. The
That
derivative of what gives you sine theta?
I got two. Negative cosine.
Negative cosine theta. And then this one, the derivative of what? Now notice, really reduce your frustration level. Really reduce it. Write this. It doesn't take very long. Write the parentheses. Write the arrow with the limits. And then ask yourself, the derivative of what gives me this? It seems like extra work, but it's the minimum because you don't screw up that much. The derivative of what gives you 1? Just be phi. All right? And then I didn't skip any steps. If I would have just wrote 2 pi in here, odds are, I'm trying to do stuff in my head, I just end up screwing up. So by writing this intermediate step, now I write 2 pi minus 0 in here. So I have a 2 pi here. It's much less frustrating. Okay. So this is a you do. Just finish this. Okay, let's see. Self-test. Normalize a wave function given in self-test 11.4. Oh, we didn't write that one down. That's too bad. I bet you that's what we just did. I bet you that's what we just did. I bet you we just did it.
I hope so.
Okay.
That'd be really sweet.
I think the answer is pi for that.
No, pi over 2. All integrations end in pi over 2.
Yeah, I think it's supposed to be 2 factorial
Self-test
over 2
11.3.
to the 2 plus 1.
This is or the new chapter.
No, self-tests are in the reading.
Yeah.
Self-test 11.4. Section 11.3.
I found it.
Oh, it is. It is.
No one has a
So
word.
self-test 11.4 is what we just did.
Nice.
Shoot, I screwed up there.
Is that in the chapter? Yeah.
It's in the reading. It's in the reading. It's actually on page. What page is it on?
297, 298.
297, 298.
Because it asks you to normalize the wave function given in self-test.
Oh yeah. Okay.
But we still have to do problems 8 and 9.
So when you get all this done, there's the answer. Right?
Yeah.
They tell you what n is. So see if you can get that. So that's on self-test 11.4 is on page 298, and that's where the answer is.
They give you the answer?
Yeah.
I want to see it. Is it square root of 1 over pi?
Nope.
Good.
No.
Good. I need something to do.
Okay, so here's 11.8 revised. Okay, so I think the only thing I revised is I changed that. Otherwise, you're doing the same thing again and again. This is a negative 2r. So in C, it's e to the negative 2r.
What is that?
Oh, problem?
Yeah, these are the problems.
And omit the-
So in C, just change C to be e to the negative 2r.
Wait, what?
Yeah. So when they want you to normalize these. So we're going to do the same thing we did. Write down, do your starting point, and just remember psi equals n phi. That's your starting point. And so this is going to be our answer. And this is what the problem gives us. They give us. So in this case, it's sine n pi x over L. Ooh, nice. No tau. Sorry, no r, theta, or phi. Okay. And so when you set this up, you're going to say 1 equals the integral, right? Psi star psi d tau. 1 has to equal, this isn't in this first question here, this first question A, right? Here they give you the range x can be between 0 and L. Do they say anything about y? Do they say anything about z? They don't give you any limits for y or z. So again, this is where these problems can be confusing, because this is not a three-dimensional problem. This is a one-dimensional problem. There is no y dimension, there is no z dimension. It's a one-dimensional problem. So my d tau is just going to be dx. So that's just something that you have to realize. That's just going to be dx. And they said the limit for it is 0 to L. Then you have to write this part. What would that look like for, we're doing A. What would that look like for A? What can we pull out of the integral? Or if you don't even want to pull it out, you can just write it, because we probably should just write it. Don't pull anything out yet. What do you put inside the integral? But have a what out front of it, though? N. So we'll take N times what? Sine, whatever they said. N pi x over L. Okay, and then the second part. So this is my psi star. My psi would be the same thing? Same thing. So we could have just wrote n square sine square. Same thing, right? Because we're multiplying the same thing twice. We can pull our n squared out. Integral of sine squared should look familiar. Right? And here's our limits from 0 to L. Okay, and it's just dx. And the reason why I know it's just dx, pretty much here's my hint. Because you really can't go by this. Because look at our last question. There's no theta or phi in here, but yet it was 3 dimensions. So they had to tell us that. And if you read self-test 11.4, they do. They say all 3 dimensions. Here, they didn't say anything about dimensions, so you just have to go by, oh, they only gave me the range of x. So 1 dimension. And then you find your normalization constant n. To write your normalized wave function, whatever you get for n, multiply it by your phi in the first place, which is sine n pi x over L, and you'll have your normalized wave function. So what that means is then you can take this, find the probability density of it, and you'll get 1. If you do that now, just using sine n pi x over L, you're not going to get 1. You might get who knows what. But you're supposed to get 1, because that's what it means. It's there somewhere. Okay, we're about out of time, so come by. I'll be glad to help you out. Yeah. Oh, there's another page?
2 problems to hand out. Yeah, use the handout. Chapter 11, day 3.
Where do you see this?
On the bottom.
We may work this and hand out in lab. Just get documents.
Assignment to be turned in for the next class period. Handout chapter 11, day 3. I don't even see it here.
It's the next page, number 12.
Okay. So you have homework. So you work on the homework and see how far you can get on the handout. We'll work on the handout next class period.
Okay. So prioritize our self-tests and our problems, and then the handout, correct?
Yeah. So just see how far you can get on the handout. That'd be good, because then you'll know what your questions are. Right? So we'll definitely be turning in the assignment here, but not the handout. Won't be turning that in.